Hello Math 125 students. I wanted to make a video where I went through one of the homework questions from 7.3 that involves completing the square and doing this full method. That's problems 5 through 8 of the homework. I do watch my previous video for just a quick recap, and I did a couple other homework questions. I'm trying to give you a little extra help here. It's a big section, but I think it's manageable if you kind of understand the recipe. But I did want to talk about completing the square. So there are several problems where, so this entire method was how to deal with things that look like this, or that look like this, or that look like this. So we learned a technique to deal with integrals that basically have quadratics. But sometimes a quadratic has a middle term. If you don't know what I mean by that, something like x squared plus 6x plus or minus something else. That has a middle term. I don't know, plus 11, I'll just make up something. So this is what I mean by a middle term. If there's a middle term, we need a way to sort of deal with it. But it turns out whenever there's a middle term, you can get rid of it. Okay, so let me briefly recap how you do that, how you get rid of a middle term. Okay, so let's erase this. And here's how I think about it. I think of what a perfect square is. So a perfect square is something like, I'll just make one up, x, I'm just doing this on the fly. Here's another perfect square, x plus, let's make something up, 5 squared. So what are perfect squares? Perfect squares look like this. These are the things you monkey face out, if you've caught me saying that in class, right? So it's this times this, this times this, this times this, this times this. This is a special product. That's what my daughter's in her algebra class in high school, they call this a special product, but you always get x squared plus the last thing squared, and then you get 2 copies of the middle thing, right? So it's negative 12x because there's a negative 6x. Similar, you get x squared plus, this is what you do if you ever forget what a perfect square is. Okay, so the point of doing that is to show you how you can generate a perfect square, and then the next point is to look for the pattern. So the pattern is, if you can get, my strategy is to make this a 1. So if you have a problem where this is not a 1, I'm just going to factor out that number. It also works for a negative 1, which you'll see. But if that's a 1 or a negative 1, then there's a certain connection you should see. And I'm going to leave this blank for a second. And I want you to think about how you could figure out what this number is just from this number, which is the scenario that we are going to encounter a lot in our problems. Like, how do we get rid of the middle term? And hopefully you see that to get from this number to this number, you have to do half. The reason it's half is because this was 2 times that number, because there were 2 copies. And then the question is, how do you get to this number? You square. So the method is half the middle squared, half the middle squared, and you add that on. What do I mean by that? So if somebody gives me a problem that looks like x squared plus, let's do it with a 12 just to really emphasize it, minus 12x plus 40. That is not a perfect square because the number that should be here is 36. And so what we do is we say, if we wanted to write this so that it had a perfect square, we really want a 36 here. But you can't just change it to a 36. So we do this clever little adding and subtracting thing. Or another way to say it is we just think of 40 as 36 plus 4. And then this is a perfect square. So then we can factor that. And that's the whole method. The whole method is to write this as a perfect square plus or minus some number. And then we can apply the method to this. Then we don't have a middle term. That's the whole idea. So that's hard sometimes for people, but ultimately what you're going to do is try to rewrite something like this as this. Then you'll make sure they're the same. And the rest of the problem you'll do like all the others we've been doing. This ability to complete the square is actually really important for several things we're going to do throughout the term and in future courses. And the technique is half the middle squared, half the middle squared, half the middle squared. Okay, so let's look at the homework. So take one of these. So you can see all of these have a middle term. Middle term, middle term. You say, well, that's not a middle term. There is no other term. But the same thing. This one's actually a fast problem. Half the middle is 3. squared is 9. And then you can write it as x plus 3 squared minus 9. And then I always like to immediately re-expand just to double check that I didn't do anything silly. Is that the same thing I started with? Yes. And so then I take the problem and I'm going to write the square root of x plus 3 squared minus 9. And I honestly don't usually do that substitution. I just go directly to the problem, meaning I would write x plus 3. I want to replace x plus 3 with 3 secant. And you can take the derivative of this and do everything like normal. Secant theta, tangent theta. And then when I go to replace, I replace this whole thing by 3 secant. And then the problem continues. So 5 and 7 really aren't that bad. 6 and 8 are a little worse. So let's do one of them. I'm going to grab number 6 and say a few things here. Let's move it over here. Give myself some more space. So here is this. So your job is to complete the square so that you can use the method from the section. There is a complicating factor here that there's a 4, there's a minus here, and there's a 4. So there's this issue. So I would come over here and I would treat this as its own problem. And I will not move forward until I am certain that I've completed the square and that the thing I have is identical to what I started with. So my personal method, and it may not be the best, if you search online you probably can find someone who has a way of dealing with the number here, but I would just factor out a 4. I just have trouble remembering other methods. So I would do that first. And then I would just focus on this. Okay, so now I am going to do half the middle, which is a half, squared, it was similar to that other question, 1/4. And then I'm going to add and subtract 1/4. Now sometimes this problem throws people off because it's a different order and because the minus. I'm always less worried about that because I know that I'm going to check my work. And I don't want to forget this 4, but right now I'm just working on what's there. So that's a 1, which is kind of nice. And then all these minuses throw people off. So I usually take a moment here and I write minus because I like to distribute the minus first because I find it easier to factor with a plus there. But I wait to do that till here. So I have 1 minus, and then this should be a perfect square. X minus a half squared. Again, it's easy to make a little sign error, but if you just quickly double check your work, this doesn't take long. Let's re-expand this. This is going to be minus x, because it's going to be that times 2, plus a 4th. And that's, if I distribute that all out, it's going to be this, minus a 4th. And the question is that the same as that? You really don't want to move forward unless you're certain it's the same. Okay, so when all is said and done, I think I've got it. I have x squared. And the whole method is half the middle squared. It's just getting it all to work out. And I've got, in these parentheses, I have a 4. And then I have 1 minus x minus a half squared to the 3/2 dx. So then I kind of stop and I'm like, okay, am I absolutely certain if I expanded out that thing in the parentheses that it's the same? And you should double and triple and quadruple check that because it's going to affect the rest of the problem. You can do something with the 4. I would take the 4 all the way out. Note that 4 to the 3/2 is 2 to the 3rd, so it's actually just 8. So I would want to write 1/8 out here. That's 4 to the 3/2. Just to make my, it's bad enough. Let's keep things as simple as we can. Okay, so at this point you could do a little substitution or you could go straight to doing the trig substitution. It's a 1 minus x case. Maybe I should do this just to make sure we're clear. If you want to clean it up even a little more before you get started, you could do this. And this is why this is a bad problem, not because of the denominator, or why it's a messy problem, I should say. It's because when you replace the x is t plus a half. And that is squared. And that makes things kind of messy. There's not really a good way to handle the numerator there. We ultimately are going to have to expand that out. So maybe I'll do that now. Let's do that. This is going to be t plus a fourth. And the bottom is going to be 1 minus t squared. Okay, so trouble ahead. There might be a way to break that up and do it, but it's like I have 3 separate problems. T squared over this, t over this. Okay. So now you kind of restart and you say, now I've got it down to a problem. You might say, I don't see the square root, but there is a square root hiding in there. It's that 1/2 power. So now I'm going to erase a little bit here. And think about what we do next. So what do we do next? It's a 1 minus t squared case, so we're going to say t is equal to 1 times sine of theta. And then you say dt is cosine of theta d theta. And the whole point of the method is that 1 minus sine squared of theta, which is 1 minus t squared, is cosine squared. So this thing is going to become cosine squared. Some people mess that up. So if you have 1 minus t squared to the 3 halves, let's just talk about that first. This is going to be cosine squared to the 3 halves. And I have seen people mess this up before, but what is cosine of theta squared to the 3 halves? If you square something and then do the 3 halves, you just get cosine to the 3rd. All right, so let's write all that out. We have 1/8. The denominator is going to end up being cosine to the 3rd. The dt is going to be cosine of theta d theta. And then the bad part, as I said, is the numerator. The numerator is kind of a test of your resilience here, but this is going to be this squared plus sine of theta plus a fourth. Oh, darn. That's why I say it's kind of multiple problems in one. Now, one of the cosines cancel, and so we can clean this up a little bit. So let's see what we can do. One of the cosines cancel. That's going to make this a 2. And so when everything is done, what I see is 1/8 the integral. And let's expand it right now. There's a sine squared of theta on top. There's a sine on top. And there's a 1/4. And you can see I'm giving myself lots of space. And they're added together. So I'm just going to separate these things completely. So I have this over cosine squared. I have this over cosine squared. And I have this over cosine squared. So that's what I meant by, unfortunately, I have 3 problems. This is just because the numerator was so messy. That's why this problem is worse. But then you go, well, why can I do those 3 problems? They look a little funny because there's all these fractions, but that should start getting you thinking, what is sine over cosine? Aha, so this looks to me like tangent squared of theta. This one is weird because it's sine over cosine, but then there's another cosine, right? Because the cosine squared. But that's really good because that is tangent times secant. That's one of the derivatives we know. And then this one is 1/4 secant squared of theta. Aha. This is in our table. This is in our table. This is not in our table, but we did this one in class the other day. So secant tangent squared is one of those that you look in the table, you're like, that doesn't work. None of the rules work. And I talked in class about what to do when that happens. You look at your identities. And there is one and only one identity in our list that involves tangent squared. And it's secant squared of theta minus 1. Plus 1/4 secant squared of theta d theta. And now we're ready. If it was me, I would clean it up a little bit. I would call this 5/4 secant squared of theta, combining the 2 secant squareds. And I would have, I don't know, tangent of theta, secant of theta, and I'd have minus 1 d theta. And to me, we're there now. This is going to be 1/8. It's going to be a plus c at the end. And this is going to be 5/4 tangent of theta, integrating. This is going to be secant of theta. This is going to be theta. And then you have one more job, which I am going to leave to you. I feel like that I've given away way too much already, but hopefully this helps you get through this homework a little better. You need to somehow return to your original variable. So the substitutions we used were t equals x minus a half and t equals sine of theta. So you can do this in two steps. You could say, okay, if t is sine of theta, then it's opposite over hypotenuse, which means this is the square root of 1 minus t squared. And so you need to figure out what tangent of theta is and what secant of theta is based off of this triangle. And then once you have that, don't forget at the very end to replace your t with x minus a half. All right, so there's a bunch of hints on that one. The other one that's bad and long is number 8. And it's the longest integral you do all term. And it doesn't even look like, it doesn't have a square root in there. But it turns out trig substitution works even if there isn't a square root. So you're just going to apply the same method, complete the square, half the middle is 1, squared is 1. So you're going to do add 1, subtract 1, complete the square. So the completing the square is a little bit nicer in this problem. But again, the numerator is messy. Okay, so expand, you'll have 3 sub-problems to do. So these are a test of your organization. I hope that helps a little bit. Let's end that here. All right.